When you first learn calculus, it's all about smooth lines, predictable changes, like figuring out the path of a ball. It's neat calculating change in systems you can actually, well, determine.
Right, deterministic systems.
Yeah.
But that's often not what we're dealing with, is it? The real world is full of noise, randomness.
Exactly. So what happens when the curve is just jagged, unpredictable, random? Standard calculus kind of breaks down.
It does. You can't just differentiate randomness in the usual way. And that gap is where Malliavin calculus comes in. It's often called the stochastic calculus of variations.
Stochastic calculus of variations. Okay. So today we're diving into that, trying to get a handle on the math of randomness itself.
That's the plan. We want to give a clear overview of what it is and why it's actually pretty important. It's basically a set of tools that takes the ideas from calculus of variations.
Which deals with functions.
Right. Deterministic functions, and extends them to handle stochastic processes, random processes.
Okay, so you mentioned Ito calculus handles stochastic processes too. How is Malliavin different? Why did we need this extra layer?
That's a great question. Ito calculus is fantastic for integration, for summing up the effects of randomness over time.
Yeah.
But differentiation, taking the derivative of a random variable, that's tricky.
Right.
Malliavin calculus gives us the mathematical machinery to actually do that, to define and compute derivatives of random variables in a meaningful way.
Sounds like a pretty heavy lift, mathematically speaking. Who kicked this all off?
Well, the credit really goes to Paul Malliavin. He started developing these ideas back in the 1970s,
Okay.
and his work led to a really significant breakthrough. It was about the solutions to stochastic differential equations, or SDEs, specifically about their smoothness.
Smoothness, like how well behaved the solutions are.
Exactly. He provided a stochastic proof using probability theory tools that something called Hermander's condition implies that the solution to an SDE has a smooth probability density.
Why is it a big deal that the proof was stochastic?
Because Hermander's original proof, it used partial differential equations, PDEs, a totally different area of mathematics.
I see.
Malliavin showed you could tackle this very deep problem entirely within the framework of probability theory itself.
Right.
It really demonstrated the power of this new stochastic approach. It was quite elegant.
Okay, so it lets us differentiate random stuff. What's the killer app? What core mathematical operation does this unlock?
The absolute key is that Malliavin calculus allows for integration by parts with random variables.
Integration by parts. I remember that from calculus. A bit tricky.
It can be,
Mm-hmm.
but it's incredibly useful. In standard calculus, it lets you shift a derivative from one function to another in an integral, often simplifying things. Malliavin does the same thing, but for stochastic processes.
So you can move the randomness derivative around?
In a way, yes.
Mm.
You can transfer the Malliavin derivative off the potentially complicated random variable onto a smoother function, which then lets you calculate things like expected values or sensitivities much more easily.
That sounds powerful. Are there specific theorems that came out of this?
Oh, absolutely. One of the really useful ones is the Clark-Ocone theorem. It gives you an explicit way to represent a random variable as a specific kind of stochastic integral.
Okay.
It directly connects the Malliavin derivative of the variable to the underlying noise driving the whole process. Very concrete.
And I've also heard about the Skorokhod integral in this context, often written with a delta symbol.
Right, the Skorokhod integral, delta den. It's defined as the adjoint operator to the Malliavin derivative. Now, for processes we call adapted, meaning they only use information from the past and present, it's basically the same as the standard Ito integral. But its real power comes when you deal with non-adapted integrands.
Things that somehow depend on the future,
It just-
mathematically, I mean.
Exactly. Processes where the thing you're integrating might depend on future information. Ito calculus can't handle those. The Skorokhod integral extends the idea of stochastic integration to cover these cases too, which is crucial sometimes.
Wow, okay, so this is building a really sophisticated toolkit. It sounds like taking this high-level math into the real world probably needs some serious expertise.
It definitely does.
Yeah.
Bridging advanced mathematics and practical tools, like an AI development or complex system modeling, often requires specialized help, which actually ties into our sponsor.
Ah, right.
Yeah, if you or your business needs support with AI training, automation, software development, or even figuring out where AI agents could best be used, you need folks who understand complex integrations. Embersilk focuses on exactly that.
Good to know. So check out embersilk.com if you're looking into advanced AI applications.
Definitely worth a look for those kinds of needs.
Okay, so bringing it back to Malliavin calculus, We can now integrate by parts with random variables. Where does this capability make the biggest impact in the real world?
Well, two areas really stand out. The first is mathematical finance. It's used quite extensively there
How so?
for computing the sensitivities of financial derivatives. The Greeks,
Hmm?
like delta, gamma, vega.
Right, measuring risk. How much a price changes if the stock price or volatility moves a little bit.
Precisely. If you're building realistic financial models that include randomness and volatility properly, Malliavin calculus gives you the rigorous mathematical tools to calculate those risk sensitivities. It's essential for hedging and pricing.
Okay, finance makes sense. What's the other big area?
Stochastic filtering. This is all about estimating the state of a system when your measurements are noisy.
Like tracking a plane with messy radar signals or cleaning up a noisy audio signal.
Exactly that kind of problem. Signal processing, control theory, anywhere you need to extract information from noisy data. Malliavin calculus provides foundational tools. And, people like Kusuoka, Strouk, Bismuth really help solidify these foundations later on. It's a well-established part of modern probability now.
So when you step back, it's kind of amazing. We take differentiation, this idea of instantaneous change we learn for smooth functions, and this whole field figured out how to apply it rigorously to pure randomness.
It really is. It shows how flexible and powerful mathematics can be.
Yeah.
It doesn't just handle the predictable stuff. It gives us a language for the unpredictable, too.
It's the mathematics of uncertainty, nailed down. Just fascinating. Well, if you found this deep dive interesting, please do subscribe to the show. Hey, and if you can, maybe leave us a 5-star review. It genuinely helps other curious people find us. Thanks so much for tuning in.